Welcome back to another lesson on trigonometry. We showed in a previous video how you can apply trigonometry to calculate the height of a tall building using the measure of an angle. So that means input an angle to find the ratio. What if we wanted to work backwards, given the ratio, to find the angle measure? For example, what if I wanted to lean my umbrella against the wall 30 centimeters away, and I wanted to know what is the angle it forms with the floor? Well, that is a case in which we could apply the inverse functions. You might see them written as arcsine theta or the inverse sine of theta. These are equivalent expressions, and same with the other two, cosine and tangent. Arc cosine of theta is equal to inverse cosine theta. Arctangent theta is equal to inverse tangent theta. So keep this notation in mind. Now, back to the question at hand. I know that my umbrella is 80 centimeters long by measuring it, and I placed it 30 centimeters away from the wall. I can use the Pythagorean theorem to calculate this height. So I will do that on my calculator. I get 74.16 centimeters. Again, Pythagorean theorem. 80 squared minus 30 squared, square root of all that gives me this number. Now this angle here is what I'm after. I'll call this theta. There are a couple different ways we can go about this. The easiest way would be to use the built-in function on your calculator. We'll get there in a minute to compare our answer, but let's explore a couple other options that rely only on algebraic operations. You'll see here that I've taken an excerpt from our trig table. From 60 to 72 degrees. Now, why did I choose that? Because we're finding the sine. Sine is opposite over hypotenuse. So we know that sine theta is equal to 74.16 divided by 80. If I plug that into my calculator, I get 0.927. Sine theta is equal to 0.927. I see that falls somewhere on my table between 0.9135 and 9335. In the past, we said theta corresponds to x and sine theta corresponds to y. Now we're going to reverse that so that sine theta is my input x and theta is my output y. Then we fall back to the same point slope form. So y equals mx minus x1 plus y1, where m is equal to y2 minus y1 over x2 minus x1. I'll plug in my values. y2 is 69, y1 is 66. x2 corresponds to those values here. So by plugging the numbers into my calculator, I come up with 149.74. Notice 0.927 is between 0.913 and 0.933. That is why I chose those two numbers. I have to bound it in the interval. Now, of course, I don't have to, but this will give me the best result compared to taking a larger interval or one that is offset from that value, as we discovered in a previous lesson. Now, this is my m. I plug it back into point slope form. Y equals my slope m, 149.74, comes from here. X comes from here, my original ratio. X1 corresponds to this, so therefore y1 must correspond to that, 66. Plug it into my calculator, and I get 68.01 degrees. That is by interpolation. What if I had chosen cosine instead? Well, cosine is adjacent over hypotenuse. So that would work perfectly fine. I just have to change a few things here. Cosine is adjacent over hypotenuse. So cosine of theta is 30 over 80, which is equal to 0.375. Notice this excerpt from our sine table includes the range in which this ratio occurs. So that's somewhere between 0.358 and 0.406. So by plugging in the numbers from the table and calculating them, I get 60.02 as my slope m. Now I'll plug that into point slope form. So y equals slope m from here plus x from here minus x1 from here plus y1 from here. Plug that into my calculator and it spits out 21.998 degrees, which rounds up to 22 degrees. Notice we were using cosine adjacent over hypotenuse for a sine table. Sine of theta is the cosine of 90 degrees minus theta. So 90 minus 22 is equal to 68 degrees, which matches our previous answer. So that exercise was simply to demonstrate it doesn't matter whether you choose sine or cosine, as long as you keep track of what you're doing. So we've done interpolation. Now you might be asking yourself, is there a Taylor series expansion I could use to find the angle measure? Yes, there is. Let's do that. Here we'll be using the Taylor series expansion for inverse tangent. Notice every term is an odd number. The coefficient 1, 1 over 3, 1 over 5, 1 over 7, and the exponents 1, 3, 5, 7. This simple representation is going to give us another way to solve our umbrella problem. So in this case, x is the ratio of tangent, tangent being opposite over adjacent. In our case, tangent of theta is equal to 74.16 divided by 30, which is equal to 2.472. Do you see a problem here? Well, remember from our video on Taylor series that if this number x is larger than 1, each time you raise it to a power, it's going to become bigger and bigger, meaning the series converges slowly. So either you have to carry out many, many terms to get the same level of accuracy, or for the same number of terms, you have a lower level of accuracy. You have to make that compromise. So what do you think we're going to do to bypass this problem? How about if we work with this angle up here? This is going to be 90 minus theta, because this is a right triangle. So if instead I do the tangent of 90 minus theta, it's going to be opposite over adjacent, 30 divided by 74.16, which gives me this number here, approximately 0.404531. This is the number x I'm going to plug into my Taylor series. I showed my work here, so take a look and see if you can follow my steps. Notice how we can roughly gauge the accuracy of our answer based on a term-by-term analysis. So here, 0.4, 0.02, 0.002, 0.0002, 0.00003. So roughly, we're gaining 1 digit of accuracy with each term. That's telling me something about how quickly my series is converging. Keep that in mind when you conduct your own Taylor series expansion. Notice I carried out 1, 2, 3, 4, 5 terms. When I did the arithmetic, it spat out this number, 0.384411. Well, what is the meaning of that? Remember, I said the Taylor series expansion for the trig functions deal with radians, not degrees. So to convert this into degrees, I multiply by 180 over pi. And that gives me 22.03 degrees. Now remember, that was this angle up here, 90 minus theta. So 90 minus 22.03 is equal to approximately 67.97 degrees. What was our answer with interpolation? around 68 degrees. So we're pretty consistent no matter which way we do this. So that may have been a bit of a long, roundabout way of solving this problem, but I wanted to demonstrate these concepts in a tangible way that would impart understanding. Quite simply, if we had plugged in inverse cosine of 30 over 80, that is adjacent over hypotenuse, we would have gotten 67.98 degrees, which matches quite closely with our result from the Taylor series expansion, and even our result from linear interpolation. So there I've shown three ways to go about it. Linear interpolation from the table, Taylor series expansion for arctangent, or simply your built-in calculator's trig functions. Thank you for watching this lesson. I'd love to hear your input in the comments section below. I will see you next time for another lesson.